Hello, in this video I am going to discuss about the conductivity of a semiconductor. So let us make one semiconductor material. For example, this is a semiconductor. It is connected to a battery. Okay, let L be the length of this semiconductor. Okay, and the area of cross section of this semiconductor is, for example, A. V is the potential difference of this battery. Then current is flowing in this direction. Current will flow in this direction. Okay, now this semiconductor material will consist of both electron and hole. For example, these green dots are the electrons, okay, and these blue ones are the holes, okay. So here this represents holes and this represents electrons. So here the conductivity will be contributed by both electrons and holes, okay. Now let we assume Ne is the charge density of electrons, okay, that is number of electrons per unit volume, and Nh represents the number density of holes, that is number of holes per unit volume of this semiconductor material, okay. Similarly, let the drift velocity of the electrons and holes are represented as, let Ve is the drift velocity of electrons. For the V, I'm representing the velocity by small v. For example, Ve is the drift velocity of electrons, and Vh are the drift velocity of holes, okay. Now we know that, as I already told you, the conductivity will be contributed by both electrons and holes. So the current will be contributed by both electrons and holes, okay. So if IE represents the current due to electrons, and IH represents current due to holes. So net current will be equal to current, for example, net current I'm representing as I. Net current I will be equal to current due to electrons plus current due to holes. So what you can write now, you can see that from class 12 we know that there is a relation between current and drift velocity, okay. You have studied in class 12. In class 12 we have studied, I guess, The relation is current I is equal to N. This relation you must have studied. This is the relation between current and drip velocity. Since it is electron, so I am representing by E. Ne means number density of electrons, as I have already mentioned here. Okay, so this represents the relation between current due to electron and drip velocity of electrons. Okay, now from here what you can write, current I divided by A, the area of cross section of the semiconductor, is equal to Ne V. Okay, now we know that current divided by area is current density. So we have got Je is equal to this. Okay, since we know that, since J is equal to I by A, we already know this relation. Current density is equal to current divided by area. Okay, now next, for example, this is equation number 1. Now we know that drip velocity is a function of electric field. Okay, since we have applied one potential difference, this is the potential difference or the voltage source between the two end of this semiconductor material. So an electric field must be produced between this phase and this phase. Okay, now that electric field we assume as E, for example. Okay, if E is the electric field between the two ends of the semiconductor, then what we will get, this drip velocity due to electron is directly proportional to the electric field. Okay, now to remove this, we put a constant. To remove this proportionality sign, we put a constant which is called as mu. For electron it is mu E. For electron it is mu E. Okay, here mu E represents mobility. Okay, mobility of electrons. Okay, so mobility in general terms we can understand. Mobility means how easily the electron can move. It's called as mobility. Okay, now this is equation number 2. Now if you put the value of VE from equation 2 to equation 1, what you'll get, Je is equal to Ne E mu E into electric field. Okay, I'm just putting the value. So what I'm getting as Ne into this. Okay, for example, this is equation number 3. So similarly, for this is for electron. Okay, this is for electron. Similarly for holes, similarly for holes. Okay, one thing I can write now before going to this step. One more step is there. From Ohm's law, we know that from Ohm's law, which is called as the macroscopic form of Ohm's law. From Ohm's law, we have, perhaps this relation you also have studied in class 12. J is equal to sigma into E. Okay, this is equation number 4. Okay, so this gives, comparing equation 3 and 4, what I am getting, sigma into E is equal to, see, I am only calculating for the electron. Okay, now then I will go for hole. So this gives sigma is equal to, okay, this is equation number 5. So we have calculated the mobility, or sorry, the conductivity for electrons. Now similarly we can write for holes. Similarly for holes, what you can write, sigma h is equal to nh, which is the number density of holes, into charge of hole. Charge of hole is equal to charge of electron, mu h. Okay, this is equation number 6. So what will be the net conductivity? Here sigma is the conductivity. Okay, so net conductivity sigma is equal to conductivity due to electron plus conductivity due to holes, which is equal to Ne plus NH, like this, which is equal to, here from here we can take okay, now for an intrinsic semiconductor means the semiconductor which is not doped. Okay, for an intrinsic semiconductor, the number density of electron is equal to, nearly equal to, number density of holes. Let this be equal to Ni, that is the number density of the intrinsic number density of electrons and holes for the intrinsic semiconductor. Okay, that is the number of electrons per unit volume is equal to the number of holes per unit volume. Okay, so here I can write here Ni into E as common, mu E plus mu H. So this represents the relation for conductivity of a semiconductor. Okay, this equation represents conductivity of a semiconductor. Okay, I hope you have understood. Thank you.